Hello, everybody. Welcome to the session on wide area networks and beyond, where we're going to hear about internet scale measurements and traffic engineering. My name is Banaz Arzani, and I'll be the chair for this session. And with that, I would introduce the first paper on 7 years in the life of hypergiants off nets. Our presenter is going to be Petros Gikis. He's currently a second-year PhD student in the computer science department at the University of College London, under the supervision of Stefano Bisicio and Mark Hanley. He is also affiliated with the Systems and Networking Research Group. His research interests are in software-defined networks, internet routing, and internet measurements. He is also looking for internships next summer. So with that, please play the video.
Hello everyone, my name is Gikis Petros and I am a second-year PhD student at UCL. Over recent years, internet traffic has exploded with the growth of streaming video. How have content providers been able to handle this surge? Today I am going to tell you how the large providers have deployed CDN caches in thousands of networks around the world and the technique we developed to track their growth over the last 7 years, when providers like Facebook and Netflix went from not having their own CDN to rivaling and surpassing Akamai for the size of their deployments. A decade ago, Craig Labovitz came to SIGCOMM' and told us that the internet is changing, as traffic is increasingly consolidating in only a few SNs. X-axis shows the number of networks needed in order to deliver the percentage of traffic depicted in Y-axis. Back in 2009, 150 SNs were accountable for the 50% of the global internet traffic. 2 years ago, Labovitz reported but half of the global internet traffic was originated from only 5 hypergiants. Such insights are great, but unfortunately require access to private data, which are not accessible to everyone. Therefore, it becomes difficult to study the infrastructure deployments that support this growth. As hypergiants, we can classify large content providers, cloud providers, and content delivery networks that are heavily traffic outbound. To deliver high-quality user experience, but also to cope with the increasing demand for content, hypergiants heavily invested in their infrastructure. A such example is Microsoft Azure Network. Hypergiants started building massive data centers and rolling out fiber to build their backbone networks. They also started aggressively peering at internet exchange points and colocation facilities, but also to peer directly with eyeball networks. However, they didn't stop there, as they started deploying off-net servers deep inside other networks to bring the content even closer to the end users. Now let's see an example and introduce some more terminology. We all know that hypergiants operate servers inside their own networks. We refer to these servers as on-nets. ISPs provide internet access to users, and in order to reach other networks, they use AS-level peering. Over the last 2 decades, hypergiants have started deploying servers outside of their own networks. These off-net deployments improve 3 fundamental challenges of the internet: capacity, latency, and congestion. Hypergiants connect on-nets and off-net servers to locally serve content to the end users. The traditional example we all think about is Akamai. Akamai sends servers to ISPs all around the world to serve end users. Other CDNs haven't been like that. They usually deploy servers near a few dozen internet exchange points in their own facilities. Wait a minute, did other hypergiants follow a similar approach as Akamai? The first thing that comes in our mind is why measuring this off-net deployment is so important. First of all, off-nets challenge the research community mental model for the value of peering. As the content is now served through the user network, less traffic crosses network boundaries. They also have implications on the modeling of internet structure. Using off-nets, hypergiants can improve their strategic position as they are able to optimize content delivery. Off-nets also make possible to deliver services in emerging networks, such as 5G, but requires close proximity to mobile users and performance guarantees. So far, the research community lacks a good understanding of the global expansion strategies. We consider that such insights can inform studies in other fields, such as economics, as they can provide insights on how major players in the internet ecosystem interact with each other. So the second thing that comes in our mind is how we can measure these off-net deployments. Traditional approaches such as IP-to-AS mapping do not work, as the off-nets use the IP address space of the hosting network. Another approach used in the past has been to use vantage points around the world, such as PlanetLab or IPAtlas, to see where they are directed for content. However, such vantage points only exist in a small fraction of all the internet networks. Thus, coverage is limited. Over the last years, researchers tried to measure them, but all proposed approaches were ad hoc and fragile to hypergiant changes. So, can we come up with a general measuring methodology that applies to all? Surprisingly, yes. This is possible as the majority of traffic nowadays is encrypted. Google reports that 95% of the traffic across its network is encrypted. To encrypt traffic on the web, TLS certificates are widely used. Certificates provide organizational information to prove ownership of a service. So any offnet hosted in another ISP should still have a certificate of a hypergiant, indicating that it belongs to the hypergiant. We will use this fact to identify offnet servers. What is even more surprising is that we can use corpuses of available TLS certificates, a dataset that was never intended for this purpose, to conduct a longitudinal study. In the rest of the talk, I will guide you through our technique, which is the first technique capable to uncover offnet footprint deployments for hypergiants. We applied this technique to historical data to study how offnet expanded in the last 7 years. We found that Google grew up by more than 2,700 ASs, but also that Facebook and Netflix launched their own CDNs, and they are now present in more than 2,000 ASs. At this point, I would also like to clarify what our work is not about. We are not doing a head-to-head comparison between hypergiants, as we don't know their business strategies, bidding agreements, and performance and cost goals. Moreover, performance evaluation is out of scope of this work, as we only focus on uncovering their offnet deployments. Now, let me guide you through our methodology. We use TLS certificates as a building block. As a first step, we clean the dataset by removing self-signed, expired, and certificates with a non-verified chain. We do this as we expect hypergiants to use only valid and public trustworthy certificates for their services. At the end of the step, the data set apart from only valid TLS certificates. At next, we use the valid certificates to extract certificates that are deployed in the hypergiant known network, but also certificates that their organizational information belongs to the hypergiant. We know that servers on Facebook network are Facebook servers, so we use them to identify what TLS certificates should be present in a Facebook server. We will later look for these certificates in servers in other networks to find offnets of Facebook. Using these certificates, we extract and construct a set of owned TLS fingerprints. We use the owned TLS fingerprints to find certificates in servers outside of the hypergiant known network that match them. The output of this step produces a set with candidate offnet server deployments. So are we done? Unfortunately, no, as the presence of a certificate in a server indicates the ownership of a service, and not the ownership of underlying hardware. For example, Facebook would use Akamai servers to run these services, or even use Akamai's offnets. Usually, hypergiants use third-party CDN servers for resilience, capacity, and to extend their footprint. Therefore, before characterizing a server as an offnet, we need to examine who owns the underlying hardware. For this reason, we use the HTTP and HTTPS headers. For example, in the case that I showed in the previous slide, the Akamai server hosting Facebook content will be running an Akamai stack, and so it will add Akamai headers to the content it serves. If we see those Akamai headers, we know it's not a Facebook offnet. On the other hand, if it has Facebook headers, it's a Facebook offnet. For this reason, we fetch the headers for all late IPs and search for specific header values. For instance, Facebook servers have an ex-Facebook debug header, but it's not present on non-Facebook servers. At the end of the step, we construct two different datasets, the HTTP and HTTPS header fingerprints. As a final step, we apply the HTTP and HTTPS fingerprints to the candidate offnet server deployment inferences from the TLS certificates and extract the final offnet server deployments. Now let's do a short recap on what we have seen so far. Firstly, a TLS certificate reveals the owner of a service. Secondly, the HTTP and HTTPS headers reveal who operates the hardware. Thirdly, using the IP address, we can classify the server as a non-net or offnet. Based on that, we can consider a server as a hypergiant offnet if a TLS certificate and the HTTP and HTTPS headers map to the hypergiant, and if the IP address is not part of the hypergiant known network. For our study, we used publicly available historical TLS data derived from the Rapid7 platform. Rapid7, on a monthly basis, scans the entire IP4 space and fetches the default certificate on port 443. We use a quarterly snapshot starting from October 2013 to April 2021. We also use Rapid7 to extract HTTP and HTTPS headers for validation. In our analysis, we examined more than 20 hypergiants, but due to time constraints, I will focus on the top 4 in terms of number of ASs. Google in 2013 had presence in more than 1,000 AS, and at the end of our analysis, Google has been in more than 3,800 AS. We also observed the birth of Facebook CDN. Facebook in 2013 had 0 OffNet presence, and by the end of our analysis, has OffNets in more than 2,000 AS. Netflix is also an interesting case, as during our study, we found that for 2 years, Netflix OffNets were using only HTTP. At this point, a general observation is that Netflix and Facebook seem to mirror Google, just lacking a few years, while Akamai seems to be pursuing a different strategy, as the OffNet footprint of Akamai reached a plateau in 2017 and then starts to decrease. To understand the impact of the server deployments to end users, we estimate what fraction of internet users in a country has OffNet side their ISP. For this, we use the ethnic population estimates per AS. In this example, we illustrate Facebook coverage in 2017 and 2021. The color on a country shows the percentage of internet users that host a Facebook OffNet within their ISP. The darkest blue is 100% and white is 0%. For example, coverage for Mexico is 90% and for Argentina is 50%. Facebook in 2017 announced plans for increased coverage in Africa and other developing regions. Our analysis shows that 4 years later, Facebook achieved this goal and also increased global coverage by 46%. The current map assumes that the servers only serve a local AS. What if they also serve the customer networks of the hosting AS? In this case, the potential Facebook global coverage increases by 27%, with the most noticeable regions being Africa, Asia, Europe, and South America. At this point, I would like to invite you to read our paper for more results. To validate our results, we surveyed hypergiants. 4 replied to our survey and indicated that correctly uncovered 89–95% of AES hosting their OffNets. Now I would like to summarize the main takeaways from my presentation today. Large coding providers serve most of the traffic on today's internet. To deliver this traffic, some of them host OffNet servers in user AES around the world. In this paper, we introduce the first generic methodology that uncovers the OffNet footprint for all hypergiants. We found that Google, Netflix, and Facebook experienced a significant growth over 7 years, but also that more than 4,500 AESs host at least one of the top 4 hypergiants. We also found that a significant fraction of users are covered by OffNets. You can get access to the software, the datasets, and explore the results through our project webpage. Thank you.
Thank you for the great talk. Let me just see if there's questions on Slack. Okay, so we don't have any technical questions yet, but I have one question for you. So in your results, what types of differences did you see in terms of how different companies are expanding their networks? And from that, what type of conclusions do you think we can make about why that they're different, or if they're the same, why do you think they're the same?
We have seen that companies like Google, Facebook, and Netflix, they seem to expand their OffNet footprint over the last 7 years, and we also see that companies like Akamai, they maintain an OffNet footprint, and we also have seen that there is a symbiosis of hypergiants in an ISP. So we have seen that AESs that host at least one of the top 5 hypergiants in the next years, where it's very possible to host even more hypergiants. So we have seen this trend. And for example, in the case of Akamai, we have seen that Akamai seems to move outside of stub AESs to small and medium AESs.
Thank you. So we have some questions in Slack. Let me ask the first one. Sergey is asking, what are the factors for extending the own footprint via going for OffNet deployments?
their own. Just a moment. The main factor is that they want to reach as closer as possible to the end users. So they want to come up as possible closer to the end users, and also to remove traffic from peering and avoid congestion of the links.
Okay, so we're out of time for questions for this talk, but you have more questions on Slack. So if you can, just go and answer them there. Please, people, if you have more questions, put them on the Slack channel, and the authors would get back to you when they have when the session's over. And with that, let me introduce the next speaker. Our next talk is going to be by Rachi Singh. It's going to be on cost-effective capacity provisioning in wide area networks with ShueFly. Rachi is a senior researcher at Microsoft. She has recently been named one of the rising stars in networking by N2 Women. She works on improving the cost and performance of wide area networks across the layers of the networking stack. And with that, could you please play the video?
Hi, everyone. Thanks for coming to the talk. I'm Rachi. I'm a researcher at Microsoft. And today I will talk about cost-effective capacity provisioning in wide area networks using ShueFly. This work is in collaboration with Nikolai at Microsoft, Sharon at Tel Aviv University, Yahweh, John, and Jamie at Microsoft. I will begin with a very high-level overview of wide area networks in the context of cloud providers. Here on this slide, I have a visualization of hundreds of data centers of a large cloud provider. These are the red circles on the map. These data centers spread across the globe are connected to each other with a private network that is called the wide area network, or the WAN. This WAN is critical to the business of cloud providers. It allows the cloud provider to meet the strict latency and throughput guarantees for their customers' traffic. The WAN consists of thousands of optical and electrical devices connected by over 100,000 miles of fiber. The yellow lines on the map represent the fiber. It takes hundreds of millions of dollars annually to operate a wide area network at this scale. And in this talk, I will show you how to reduce the cost of provisioning capacity in the WAN by 40%. I'll first zoom into the North American part of the cloud WAN. I'm showing you a simplified view of the WAN with 3 geographical regions. The names of these regions may be familiar to you. So this is US West, US Central, US East. Underneath this interregional layer 3 topology, cloud networks operate what are called point-to-point optical backbones. What this means is that each regional router connects to an optical terminal or an optical switch. These optical terminals route wavelengths of light onto the underlying fiber. In a point-to-point backbone like this one on the slide, a wavelength of light originates at a region. It traverses on the long-haul fiber path until the neighboring region, where it is converted from optical to electrical domain. Once the signal is converted to the electrical domain, it can be routed as per decisions made by a layer 3 traffic engineering controller. Then, signals are converted back to the optical domain. This process of converting a signal from optical to electrical and back to optical domain is called an OEO conversion. Finally, the wavelength is routed back on the fiber until it reaches its destination. What I want to note here is that all wavelengths in a point-to-point network undergo optical to optical conversion at nearly all intermediate hops on the path toward their destination. Like in this example, the wavelength originates at US West, undergoes an OEO conversion at the intermediate US Central region, and finally terminates at the US East region. This design of cloud WANs was not accidental. It was a well thought out design because it keeps the smarts of routing at layer 3 while keeping the physical layer as simple and uncomplicated as is possible. But here is the disconnect between the design of point-to-point optical backbones and the traffic that they carry today. In this graph, on the x-axis, I'm showing the 3 types of traffic that can be observed by regions in the cloud WAN. These are traffic that originates at a region, traffic that terminates at a region, and traffic that passes through or transits a region. The y-axis shows the percentages of each traffic type observed by geographical regions of a large commercial cloud provider. As you can see, 60% of traffic observed at any region is simply passing through. This traffic neither originates nor terminates at the region. Traffic that is simply passing through a region does not need conversion to the electrical domain, only to be converted back to the optical domain. Such OEO conversions are wasteful, and let me show you why we should care about these wasteful OEO conversions. This is a photograph of a chassis-based switch used to connect regions in the cloud WAN. Every unnecessary OEO conversion occupies scarce and expensive router ports on the line cards of the switch. And I've highlighted one such port in the slide here. OEO conversions use transponders that plug into the line card ports, occupy ports on the optical switch that connects to this line card, and consume power. Thus, undergoing OEO conversions is expensive because each conversion uses tens of thousands of dollars worth of hardware equipment that contributes to the majority of the cost of provisioning capacity in the WAN. So hopefully I have convinced you that there is an opportunity here to save the cost of provisioning long-haul capacity by preventing wasteful OEO conversions. Our proposal is to optically bypass regions in the WAN where OEO conversions are unnecessary and uneconomical. And by optically bypassing a region, I mean to skip OEO conversions wherever possible, keeping the signals in the optical domain for as long as is possible. However, enabling bypasses in the wide area backbone is challenging. A key challenge is that signals that bypass geographical regions have to travel longer distances on the fiber before getting regenerated. Longer fiber paths lower the signal quality, and lower signal quality is bad for the signal's data rate. Let me show you this with an example. I'm bringing back the same three-region network in this diagram. The light signal that was originating at the leftmost region now bypasses the central region and terminates at the rightmost region. Previously, the signal was undergoing an OEO conversion at the central region. An OEO conversion regenerates the optical signal, correcting errors that had occurred during transmission on fiber. However, optical bypass prevents OEO conversions, so now the signals don't regenerate on intermediate hops. Due to longer distance on fiber before a regeneration, the signal undergoes more attenuation and dispersion. For a detailed explanation of the relationship between the fiber distance and signal quality, please check our paper. So to develop a bypass-enabled cloud backbone, we need to identify which wavelengths can bypass which geographical region, taking into account the decline in signal quality due to increased fiber distance. In the following slides, I will present my solution to this question, but at a high level, we can break the solution down into three main steps. The first is that we will enumerate all possible instances of optical bypass in the cloud network. Secondly, we will prune the space of possible bypasses by applying physical constraints on distance and signal quality. And finally, with the remaining feasible bypasses, we want to select the ones that maximize the cost savings but do not hamper the network's capacity. So here's the first step. We want to enumerate all bypasses. To show what this means, I will use a simple example where I'm representing the interregional backbone with a 5-node graph. There is a wavelength lambda that traverses from region A to B and then from B to C. We want to configure an optical bypass where lambda bypasses the region B like so. This is what I mean by one optical bypass, a combination of wavelength and region that participate in the bypass. Once we make this change to the network connections, we save 2 router ports on region B due to the bypass. while the underlying fiber or equipment did not undergo any changes. The network layer topology after this bypass is implemented has a new direct edge between A and C. This edge is what the bypass of lambda has created. So we can view bypasses as network shortcuts. These are the new edges that are created in the layer 3 topology if bypasses were to be implemented at the physical layer. So we can enumerate all potential bypasses in the cloud network using this network shortcut abstraction. For example, the shortcut AC introduced by the bypass of region B is a 3-hop shortcut. Similarly, we can enumerate all 3-hop, 4-hop, and 5-hop shortcuts. It turns out we don't need to enumerate shortcuts longer than 5 hops because bypassing any more regions causes the signal quality to become too low to be useful. The length of a shortcut's fiber path determines the data rate of wavelengths participating in the bypass. If a shortcut has greater than 5,000 kilometers of fiber distance, it becomes infeasible due to lowered signal quality because of transmission on such a long distance. All these physical constraints help us prune the space of network shortcuts. Let me show you how many shortcuts can be pruned in this manner. Here, I have a distribution of fiber distance or length of shortcuts that we've enumerated, split by different hop lengths. Over 50% of the shortcuts are longer than 5,000 kilometers, and thus we can prune them. So despite the large space of potential bypasses, we can prune away the bypasses that are physically impossible due to constraints on fiber distance. After pruning the set of bypasses, we are left with a set of potential optical bypass opportunities in the WAN. Using these potential shortcuts, we can augment the network topology with new edges that would get created if the corresponding optical bypass is enabled. If you recall, these new edges are the network shortcuts that we were trying to enumerate. But we still don't know how many wavelengths can participate in these bypasses. Or in other words, what is the capacity of the network shortcuts that are feasible? We determine the capacity of each feasible network shortcut by allocating traffic demands on this augmented network topology. Allocating demands on a network topology is exactly what traffic engineering problems do. However, our objective of allocating these demands is different. We try to maximize the traffic allocations on the shortcuts that we augmented the topology with. By doing this, we are essentially siphoning traffic off of the network edges to these shortcuts, thereby deciding the capacity of the network shortcuts. As a result, we identify the wavelengths involved in all feasible optical bypasses such that existing traffic demands in the network continue to be met while the cost saving through bypasses is maximized. For more details about our optimization formulation, please check our paper. I'll give a very brief preview into the cost savings enabled by ShoeFly. We evaluate ShoeFly on the Microsoft Swan network topology and use real data from the network as input. This includes the traffic demand matrices and signal quality measurements from the production network. In this graph, I will present the percentage of router ports that can be saved by implementing ShoeFly proposed optical bypasses. And I'm breaking these results down into savings enabled by bypasses of different hop lengths. These bars show the percentage of router ports that ShoeFly can save when enabling bypasses. And as you can see, ShoeFly can save up to 43% of the hardware cost of provisioning capacity in the current network topology. We also show that the logistical burden of enabling ShoeFly is quite low. In fact, 25% of the instances of optical bypasses proposed by ShoeFly can enable 80% of the total cost savings. I will conclude this talk with a summary about ShoeFly. ShoeFly designs optical bypass-enabled cloud backbones. It maximizes the cost savings through bypass. In fact, we show that ShoeFly can save 40% of the hardware cost of long-haul capacity. While we did not discuss this in the talk, Shoofly ensures that the bypass-enabled backbone is resilient to both stochastic and deterministic link failures. And finally, Shoofly's bypass suggestions are future-proof. The cost-saving potential does not diminish even when network demands increase to 8x the current network demands. For more details, please check our paper. Thank you.
Thanks, Rachi. So you already have questions on Slack, and many of them, so we're not going to get through all of them. But the first one is from Ying. He says, nice talk. What is the reason for having the intermediate IP hop in the original design? Is it cost or optical distance constraint?
I try to answer this in the Slack as well, but I think part of the reason is that the key insight, which is the empirical insight about how the backbone is being utilized with the current traffic demands, is something that we could only learn after operating it for a significant amount of time. So originally the backbone is designed such that we're more flexible to meet any new demands that show up. But now that we've sort of settled into these regular predictable patterns, it makes more sense to have the backbone kind of cater to the kind of demands we have. So it's more of, now that we've done this for a while, what can we change, as opposed to we knew this from the beginning.
So your next question is from Zhizhen. He's asking, in your problem formulation, by avoiding OEO conversions with optical bypass, besides the OSNR deterioration challenge, it also creates another optical layer wavelength continuity constraint problem. Usually this wavelength continuity, usually this wavelength continuity will result in fragment and spectrum occupancy, and hence greatly reduces the number of available wavelengths on the bypass shortcut path. How do you factor in this optical layer wavelength continuity problem when creating optical bypass as shortcuts?
So that's a great question. And absolutely, wavelength continuity is a constraint that we thought about a fair bunch, and then we decided to not really add it into the formulation. And part of the reason for that was, in its current form, the way the backbone is being used, we're really not, so fragmentation of the spectrum is not a problem that we are currently facing. And even at the prospect of deciding a small set of bypasses to enable, it didn't seem to be an operational concern. And as a result of how our co-authors who actually maintained this backbone, how they felt about this, we decided to not add wavelength continuity constraints. But it's something that we thought about and we continue to think about actively. And it's a really great point. Thank you.
Thanks, Rachi. So we're out of time, but you have many more questions on Slack to answer, so please do that.
Thank you.
Our next speaker is going to be Varun Gupta. He is talking about a capacity efficient and uncertainty resilient backbone network planning with HOST in the Facebook network. Varun is at Facebook and currently working on problems related to modeling and optimizing Facebook's production backbone network. His research interests include systems, large-scale optimization, and ML-based approaches for solving combinatorial optimization problems. And please play the video.
Hello, today I'll talk about the network planning process at Facebook and how we are using host-based planning for building an efficient and uncertainty-resilient backbone network. Facebook's backbone network interconnects tens of data center regions, and each region can contain multiple data center buildings. It also connects hundreds of points of presences and has a global footprint that connects billions of people to our services. In recent years, the backbone traffic has been growing at a rapid pace. This growth is especially more pronounced for machine-to-machine traffic within the network. This growth has prompted us to look for new methods for planning and building our backbone network. The backbone network delivery process starts all the way on the left with a forecast for future demand. This forecast is then consumed by a network planning process that provides signals of how much fiber to procure and where to procure it. It also guides the design of IP and optical network and hardware deployment. Finally, once this deployment is complete, circuits are provisioned and traffic can flow in the network. Today, I'll talk about the network planning process and how it works at Facebook. In the rest of the talk, I'll first introduce the network planning process, and I'll talk about the challenges we face in planning and why we are moving towards host-based planning. Then I'll talk about the system design, performance of our system, and some learnings from operating and deploying the host-based planning model in our production backbone. Traditionally, planning relies on ingesting the network topology and a pairwise source destination forecast of flows in the network. This forecast is then coupled with a policy of how to protect flows under failures, and all of this information is used to identify a cost optimized network build plan, which provides signals about how much capacity and where to turn it up, how much fiber to procure and where to procure it, and finally quantify the growth of space and power at different sites. Here we show a small example of planning. We start with the given fiber footprint. The IV topology consists of nodes and links that can traverse multiple fibers. Traditionally, demand volumes between each source and destination pair are known. In our toy example of 3 nodes, there are 2 flows of 1 Gbps each between nodes A to B and A to C. Consequently, we need to turn up at least 1 Gbps capacity on links A to B and A to C to get a cost optimal design with 2 Gbps total capacity. Typically, a group of fibers and nodes in a topology can fail, and these failures propagate across layers. In our example, if a fiber around node B fails, the link between A and B will fail. For network resilience, we need to provision enough capacity on alternate routes. For the red flow, A to C and C to B is a valid route, and thus we add 1 Gbps additional capacity each on link A to C and B to C. This gives us a cost optimal design with total 4 Gbps capacity. Operationally, there are several challenges associated with planning such a large backbone network. In practice, services are migrated from one DC to another for various reasons, example load balancing, service scaling, latency reduction, etc. Therefore, the industry-wide trend is to decouple service logic from infrastructure design so that services can use infrastructure more flexibly. This requirement makes accurate point-to-point traffic demand forecasts between site pairs very difficult. Consequently, networks need to be overbuilt to account for sum of peaks between each site pair. In addition, for an actively growing Facebook network like Facebook's network, new DCs are built yearly. It is almost impossible to estimate the traffic demand between DCs that are yet to be built. In the next slide, I'll talk about how host-based planning can help mitigate some of these challenges. This toy example demonstrates a common scenario in our network. For a source node S1, the traffic to node S2 and S3 can peak at different times. Example, 2 Gbps for S2 in the morning and 3 Gbps for S3 in evening. The total demand, however, which is the sum of peaks seen in the network from S1, is then 5 Gbps. However, since the underlying hardware at node is limited, the total demand always stays below 3 Gbps. Now we showed how the intuition of previous example translates in practice to a production network. Here we show the total demand for a pipe model versus hose model for 1 month of Facebook's North America network. We calculate the daily peak traffic for a node in the network. The daily peak is defined as the 90th percentile of traffic observed during the busiest hour. We see that the daily peak in hose model can be 10 to 15% lower than the pipe model, which can incur significant capacity savings. Next, we look at this from the perspective of reducing uncertainty. We plot the CDF of peak demand for pipe and hose model at the same site. We normalize the absolute traffic volume against the maximum demand in the network. Assume that we plan for 55% of maximum total demand, as shown by the blue vertical line. Then, under the hose model, the daily peak demand will be satisfied for 90% of the days, while it will be satisfied only 40% of the days for the pipe model. Now that the benefits of a host-based planning model are clear, we can talk about how such a network can be designed. There are 2 main challenges that we address in this paper. First is that the physical realization of the capacity in the network is still point-to-point. Thus, we need some way of translating the host demand to per source destination pair demand. Second is how we can leverage this possibly large number of realization of point-to-point traffic to get a cost-optimal design. Our host-based planning system consists of several modules that are production-grade software running for planning a backbone network. A traffic forecast generates a demand forecast based on providing services. This forecasts are then used by a capacity planner to generate long-term and short-term network plans. The capacity planner consists of 2 components of the system. Number 1 is a traffic matrix generator engine that identifies the set of traffic matrices that drive additional capacity in the network. And number 2 is a capacity optimizer that consumes the traffic matrices and failure scenarios to generate cost optimal plans. Next, I'll talk about how we generate traffic matrices from the host forecast. Host traffic forecasts can be thought of as constraints that form an n-dimensional convex polytope. Any point inside the polytope is a valid traffic matrix. Since there are infinite number of such matrices possible, our goal is to identify the matrices which are important for planning. We call these matrices as dominating traffic matrices, and these are matrices that are likely to add capacity in the network. A traffic matrix generation process starts with randomly sampling a large number of traffic matrices from all these possible realizations. To identify a dominating traffic matrix from the sample traffic matrices, we rely on the intuition that dominating traffic matrices will add capacity on bottleneck links in the network. We can identify these bottleneck links by looking at graph cuts. We rely on a sweeping algorithm to quickly find graph cuts in the network. While we sweep the network, we define a parameter called edge threshold, which dictates how many cuts we'll find, and if a flow cross across a cut for a traffic matrix is larger than other traffic matrices by a certain parameter called flow threshold, we call this traffic matrix a dominating traffic matrix. To measure how well our dominating traffic matrices cover the possible space of traffic matrices, we define a metric called coverage. At a high level, this is a measure of volume of convex hull containing all samples divided by the volume of the total host space. We plot the number of traffic matrices for different flow slacks and different edge thresholds on the graph on the left. We also plot the coverage that these traffic matrices achieved as shown in the graph on the right. The key takeaway is that for production topologies, we can find about 200 traffic matrices that achieve 70 to 80% coverage. This means that we can achieve high coverage with a reasonable number of traffic matrices. The dominating traffic matrices are used by the capacity optimizer to solve both short-term and long-term planning problems. The short-term planning outputs the exact IP topology, that is the IP links and the capacity on each link, while long-term planning only determines the fibers and hardware to procure. For both short-term and long-term planning, capacity problem optimizer solves an underlying large integer linear program whose overall objective is to minimize the cost. The cost consists of fiber procurement, deployment, and cost incurred in turning up already procured fiber. There is also cost associated with turning up IP capacity. The constraints in the problem are how much spectrum is available, any routing constraints, and finally QoS constraints for different flows determined by a planning policy. We solve the optimization problem through commercial IP solvers and several heuristics. More details for this are available in our paper. Now I describe the performance of end-to-end host-based planning system for a production topology. In this graph, we show the yearly capacity growth from 2021 to 2025 for both host-based and pipe-based planning model, and this is shown as a percentage of our baseline capacity for our North American network. We use the total IP capacity and number of fibers as a stand-in for the total network cost. Our results show that host-based planning can reduce up to 17% capacity over the next 5 years in Facebook's network. We also measure the impact of demand uncertainty through a what-if analysis. We measure the unrouted demand in the network for a period of 1 month, assuming that the network was designed from a demand prediction that was forecasted 6 months ago. We notice that 80% of days, pipe-based demand can lead to 50% more drop traffic than a host-based plan. But since there is always some slack in the actual network, this is unlikely to happen, but this gives a useful production estimate of the demand uncertainty in the network. Finally, we'd like to share some experiences from deploying the host-based planning over the past few months at Facebook. Host-based planning has allowed us to simplify how we plan for disaster and catastrophic failures in the network. Disaster recovery plans identify how requests will be migrated under a disaster, and each mitigation plan will create a drastic shift to the original traffic matrix. For a network plan with pipe, it requires careful evaluation of every traffic matrix and certify if it can be accommodated by the backbone. By moving to a host-based network planning, we are able to instead provide an upper bound on the total ingress and egress traffic supported by per DC. During the deployment of host model, we also learned that network-wide host model can be an overkill. This is because general services which consume a large amount of network resources communicate to a subset of DCs. Taking service placement into account while host-based planning can help reduce the scale challenges associated with host-based planning. We also discovered that testing network plans using demand forecast and modeling assumption for production network is non-trivial. The actual performance only becomes clear several months or even years after the plan is deployed. In practice, we rely on extensive A/B testing and manual verification by experts. We encourage more research in this area. Finally, we observe that while complete demand shifts are rare, moderate shifts of 30 to 50% traffic between different regions are still common. This leads us to choose 80% host coverage as a target metric for our planning process. To summarize, we show that how host-based planning can save significant network capacity and reduce demand uncertainty. Our projections indicate that host-based planning can save up to 17% in the backbone capacity for Facebook's network. We also describe algorithms that can help scale host-based planning to a large production network and discuss operational challenges plus lessons learned from the adoption of hosts. Thank you.
Thank you. So let me just check Slack real quick. Okay, so while we're waiting for questions, I had one of my own. So it seems like the difference between the pipe model and the host model that you're observing is mainly coming from the convexity of the max function. And I was sort of wondering if there's a broader observation you can make by what are the properties of functions that you can apply to the history of traffic matrices and the relationship with the quality of the traffic engineering that you can get from your network and how you plan the network. Do you know what do you recommend for researchers who want to study this space?
Yeah, that's a good question. I think some of that we are kind of taking into account, like how the historic traffic matrices look like. And for us, it kind of already falls into the kind of the host forecast we have. So the host forecasts are like kind of sum of egress and ingress capacities at sources and destinations. And we kind of say that, okay, this all possible traffic matrices will be reflected in some of these forecasts that we're getting. And then it kind of becomes a question that how good you are breaking these traffic matrices down using the kind of the algorithm we describe in the paper. So as long as that process is good and it guarantees you sufficient coverage, I think we should be good there. But yes, definitely this is a topic of future research, like how it will kind of behave in production over a long term and over like different traffic matrices.
Thanks. And we're starting to have questions in Slack. So the first one, Sanjay is asking, can you elaborate more on what you are using A/B testing for and what the issue is in this context?
Yeah, so the A/B testing is basically for acceptance of like different plans we generate. So we have one way of doing this, which is like the pipe-based model, and then if we deploy host-based models, which we are doing right now, we have to kind of make sure that these models will cover all the traffic matrices like we are talking about right now. So that's where the A/B testing of different plans come from. We have to talk to domain experts and people who are actually building the network to make sure that's acceptable.
I see. The next question is from Matt Calder. He's asking, nice work. Can you mention how often you reevaluate your capacity plan?
Yeah, so that's we have different horizons of planning, short-term and long-term. What I will say is the short-term is very frequent, or kind of periods of months. Long-terms are done like over a period of years.
And I think we have time for a couple more questions. So the next one is also from Matt. He's asking also, how do you incorporate inorganic demands?
Inorganic, sure, maybe I don't understand that very well. Maybe I can follow up on Slack about that.
Yeah, and the next one is from Ajay. He's asking, what was the measure of quality of plan? Do you look throughput or latency or traffic matrices to see the improvements?
Yeah, so the measure of the quality is the cost of the plan, and how we kind of latency obviously is one more metric there. And we also kind of want to make sure that we are not kind of overcompensating on cost, that there is some slack in the network to handle like all the traffic matrices that maybe we haven't planned for. So that those kind of things we look at.
Thank you. Okay, so I think we're out of time, but you have more questions on Slack, so if you can please go and answer there. Also, for those of you who are pasting questions in Zoom, I'm repasting them in Slack, so if you want to see what the authors have to say, please go check there. With that, let's talk about our last paper of the session. So Zhishan Zhang is going to be presenting the paper Aero on co-optimizing the optical layer and traffic engineering in the IP network. Zhizhen is a postdoc researcher at MIT CSAIL with Manya Gobadi. He received his PhD and bachelor's degree in electrical engineering from Tsinghua University. His research interest lies in the electrical/optical cross-layer design of network systems that enables reconfigurable wide area networks and machine learning systems.
Hello, everyone. I am Zhizhen Zhong, a postdoc researcher at MIT CSAIL with Professor Manya Gobadi. Today, I'm going to talk about our work, Aero, Restoration-Aware Traffic Engineering. Wide area networks are the workhouses of today's global internet services. All major online service providers like Comcast, AT&T, and Google own and operate their private WANs. All these global scale backbones are built using optical fibers across continents and oceans. Because building and maintaining a global scale network costs billions of dollars, it is important for WANs to be efficiently utilized. In this talk, I will present a novel system that improves the network throughput by a factor of 2 without compromising availability in large-scale WANs. But this is not easy. It is very challenging to squeeze more throughput from a globally deployed network. In the following slides, I'm going to walk you through several important building blocks to achieve this goal. Let me start with the impact of fiber cards on WANs. How are optical fibers related to WAN links? What is a WAN link? Let me give a simplified example. Assume that we have an IP link between Boston and San Francisco. This IP link can transmit data between router ports. If we zoom into one end of this IP link, we see that right after the router ports, there is a device called optical transponder that converts the signal from electrical domain to optical wavelengths. After optical transponders, we use optical switch to add, drop, or switch optical wavelengths in the optical fiber network. On the fibers, we place optical amplifiers every 80 kilometers to compensate power attenuation during signal propagation. Therefore, an IP link between Boston and San Francisco is actually a logical connection supported by provision wavelengths or lambdas on fibers. Operating a global scale WAN while maintaining availability is challenging, mostly because of unexpected failures, especially fiber cuts. There are many reasons that lead to fiber cuts, such as disasters, construction works, or even animals. How severe are fiber cuts? To quantitatively answer this question, we study the impact of fiber cuts on a global scale WAN. Each peak in this figure represents a fiber cut event. For a city pair, we observe that fiber cut events happen almost every month. If we zoom into one of the events, approximately 8 terabit per second capacity is lost for 9 hours until the fiber is repaired. This is a massive loss for the IP layer capacity. If we consider more city pairs in the network, we find fiber cuts take down several terabit per second capacity quite often. The question is, how do we solve this problem? Well, the state-of-the-art approach to cope with fiber cuts requires adding backup links. On this 4-node topology, to handle fiber cuts and avoid traffic loss, the state-of-the-art approach adds redundant wavelengths, backup lambda 1 and backup lambda 2 on the optical layer to create backup IP link 1 and backup IP link 2. In this case, when fiber BC is cut, the network is still available. However, this approach requires redundant network hardware like router ports and transponders. Now we know that fiber cuts have a huge impact on WANs, and the state-of-the-art approach is very inefficient as it requires actual router ports and transponders to build backup IP links. Our work goes beyond the state-of-the-art by unlocking the opportunity to restore failed IP links. Let me show you how we achieve this. We propose Aero to reduce redundancy while maintaining network availability. Aero is the abbreviation for Agile Restorable Optical Wavelengths. Different from the state-of-the-art approach, when fiber cut happens, Aero achieves the same availability goal by reconfiguring the wavelengths from broken fiber to healthy fibers to restore the lost IP capacity using the same network hardware without redundant router ports and transponders. The next question is, how to plan IP optical restoration for Aero? A straightforward solution is to separate the optical layer from the IP layer. By iterating over all plausible fiber cut scenarios on the optical layer, we calculate the restoration plan for each scenario that maximizes the total restore capacity in an offline manner. Then, we feed the per scenario restoration plan into the traffic engineering formulation to optimize traffic flow allocations. An immediate question to answer is there enough room in the optical domain such that for every fiber cut scenarios, we can reconfigure all affected wavelengths? To quantitatively answer this question, we calculate the restoration ratio of each fiber in a large-scale WAN and plot the cumulative distribution function of the restoration ratio of all fibers in this figure. We observe that 62% of the fibers are only partially restorable. How does this partial restoration affect our goal of reconfiguring the failed wavelengths from broken fibers to healthy fibers? For instance, in this case, if the middle fiber is cut, we want to reconfigure the wavelengths to the top and bottom fibers. If lost wavelengths can be fully restored, then the only decision is to reconfigure all the wavelengths to revive the entire IP layer capacity loss. The decision is simple, and this is the beauty of layering in the Internet architecture. But remember that in the last slide, we talked about a majority of the fibers are only partially restorable. It means we cannot restore all the lost wavelengths, and we have to be intelligent when deciding which IP link to restore, or equivalently, which wavelengths to reconfigure. Let us consider a partial restoration scenario where we can only restore 3 wavelengths on the top fiber and 2 wavelengths on the bottom fiber. In this case, there are many partial restoration candidates. All of them achieve the same amount of restored capacity on the optical layer. For WAN operators, when multiple restoration candidates restore the same amount of lost capacity, they care more about which one can actually satisfy more traffic demands or throughput on the IP layer. As a result, when restoring failed IP links, we need to consider both IP layer real-time traffic demands and optical layer restoration candidates for optimal network throughput. Therefore, to handle partial restoration, the question is, when full restoration is not possible, which partial restoration candidate leads to the best network throughput? In response, Aero devises a novel lottery ticket abstraction to augment IP layer traffic engineering with optical layer restoration awareness. In the following slides, I'm going to present the Aero traffic engineering system that dynamically restores failed IP links under fiber cut scenarios. To select the optical layer restoration candidate that has the maximum network throughput, the ideal solution is to formulate the problem into a cross-layer IP optical traffic engineering formulation. This formulation jointly considers the traffic demands and network topology on the IP layer. It also takes the optical layer topology and fiber cut scenarios into account. Theoretically, this cross-layer formulation can find the optimal traffic splitting ratios on the IP layer and the optimal restoration candidate on the optical layer. However, the problem with this cross-layer formulation is that it is an integer problem and contains billions of variables for today's WAN topology, making it computational intractable. The root causes for the computational intractability of the cross-layer formulation are that the IP and optical layers are orthogonal. Hence, formulating a cross-layer problem will result in a huge expansion of problem space. Another important factor is the mapping between IP links and their corresponding wavelengths is a binary decision variable. Therefore, it makes the problem to be integer and NP-hard. To solve this problem and avoid excessive computational complexity, Aero proposes to abstract the optical layer and only feed essential information into the IP layer. We first solve the optical layer integer problem in an offline manner and record the failed IP link's restorable capacity as lottery tickets. After that, we feed these lottery tickets into the IP layer traffic engineering and solve the T only on the IP layer to achieve a reasonable problem space. With the lottery ticket abstraction, we design Aero traffic engineering system. We first generate multiple restoration candidates using a modified randomized rounding algorithm for each failure scenario and represent them as lottery tickets. Basically, The lottery ticket abstracts the details of wavelength reconfiguration on the optical layer and only contains essential information on how each failed IP link could potentially be restored. Then, we feed this abstracted information into the Aero TE formulation on the IP layer. Because of our lottery ticket abstraction, Aero's restoration-aware TE formulation is a linear program, hence can return traffic splitting ratios on the IP layer and restoration plan on the optical layer with fast runtime on today's WAN topology. Finally, we evaluate the gains of restoration-aware WANs. We build a production-level optical network testbed to emulate part of the production WAN. It includes 4 optical switches connected by over 2,000 km optical fibers. On these fiber links, we deploy 34 amplifiers. We also deploy 16 pairs of optical transponders to provision wavelengths on this testbed. We run a fiber card restoration trial on the testbed. Initially, there are 16 wavelengths running on the optical layer, supporting the IP layer topology of 4 IP links. We simulate a fiber cut scenarios where the fiber between C and D is cut. Therefore, 14 wavelengths that are running on this fiber are failed, and their corresponding IP links, AC, BD, and CD are lost. We then use the key idea of Aero to reconfigure the failed 14 wavelengths to healthy fibers. Our experimental results show that, compared with state-of-the-art approach, Aero can reduce the reconfiguration delay from 17 minutes to 8 seconds. We run large-scale simulations on 3 WAN topologies with different network sizes. For B4 and IBM topologies, we use traffic matrices generated from SMORE. For Facebook topology, we use real traffic traces from production measurement. We use a combination of fiber destroying and k-shortest path routing for tunnel selection. We compare Aero with state-of-the-art failure-aware TE algorithms, FFC and TWAR. We also compare with ECMP as a baseline. The key metric in evaluating the performance of a WAN is the availability of the network. In this figure, a better TE algorithm should be able to sustain high availability at a larger demand scale. We consider several TE algorithms. For example, FFC can sustain at least 99.9% availability when demand is scaled by 2.1. When the demand scale is larger, FFC's availability performance quickly drops below 99%. TWAR and ECMP perform similarly. We observe that Aero can support twice more demand with the same level of availability than prior TE approaches. By reconfiguring wavelengths to restore failed IP links, we can support twice more traffic while maintaining a highly available network. Note that the throughput gain is achieved without adding more redundancy on the IP layer. This massive gain of throughput in Aero is the result of 2 important properties. First and foremost, Aero is able to restore failed IP links and bring lost capacity back after failures. Secondly, Aero's lottery ticket enables the traffic engineering system to navigate the vast possibility of optical restoration candidates and select the best restoration candidate based on real-time traffic demand. For instance, if we only had 1 lottery ticket, the gain would have been only 15%. Most of the throughput gains come from the lottery ticket design. In conclusion, Aero is a traffic engineering system that reconfigures wavelengths during fiber cuts. When restoration is done on the optical layer and TE is done on the IP layer, our lottery ticket abstraction makes cross-layer traffic engineering feasible at large scale to meet the stringent TE runtime requirements. Our experiments show that Aero supports 2 to 2.4 times more demand without compromising availability. Our code is available online, and we welcome more colleagues in the community to join us and explore the new exciting opportunity on the optical layer together. Thank you for your attention.
Thanks, Shijin. Let me check Slack. Okay, while we're waiting for question, I'll ask you one question that you and I actually talked about before, but I think maybe it would be of interest to others as well. So you do a relaxation of an integer linear program to solve your traffic engineering problem at the end after having used lottery tickets to reduce the size of that program. So if you're using a relaxation, why not just relax the original ILP instead of having to go through all of these additional steps to come up with a different ILP using lottery tickets? And you're muted, Jijan.
Okay, thanks, Vanas. This is a great question. So actually, our lottery ticket design is not a relaxation of the initial ILP. So we actually design abstraction to solve the problem. The root cause or the reason for this is we try to just relax the ILP into ILP. And because of the huge problem space, the runtime of the relaxed ILP is still very long. It's longer than the key requirements of several minutes. So that's the reason that we need this lottery ticket abstraction for the problem to be solved very fast.
Let me check Slack again. If not, I can ask you one more question. Yeah, so we don't have more questions on Slack yet, but another question I have is, what are the implications of not having any guidance on optimality gap? So you don't do an empirical evaluation against optimal, nor do you have a theoretical guarantee of what the optimality gap might be. So do you have any intuition on what types of traffic matrices and scenarios may cause significant optimality gaps, or under what situations you might run into significant optimality gaps?
Yeah, thanks, Vanas. This is again a very great question. So as we discussed in the paper, like this is a randomized algorithm. So we really depend on the randomized algorithm to have this abstraction. And we do have a probabilistic guarantee in the paper, but I didn't include that in the talk because of time. So if you are interested, like readers can go to the paper and read the probabilistic guarantee. And the intuition is like, as I show in the results section, so if we only have one ticket, the performance gain wouldn't have been so impressive. So the number of lottery tickets really matters. And this is the fundamental nature of the randomized algorithm. If we increase the opportunity pool, then we get more chance of having more performance improvement.
Thank you. Let me check Slack one moment. Okay, so Sanji is asking you, nice work. I was impressed by the production testbed. Is this something that the community can use?
Yeah, this is a good question. So this paper is in collaboration with Facebook. So we were actually running the experiments with the.
I lost your voice. I don't know if that happened to everybody.
Yeah, it's muted for me as well.
Yeah, sorry. So, okay. Since we're out of time, Zhijian, you will probably have more questions in Slack, so please go there to answer the rest of the questions. After this, people stick around. We're going to have a fun trivia event that the SIGCOMM group has planned for you. And thank you for attending the wide area networking sessions, and the authors will be on Slack to answer any other questions you might have. Thanks.